All right, in AP Calculus, we study two different branches of calculus. We study differential calculus and integral calculus. Differential calculus is just a study of derivatives. Integral calculus is a study of integrals and integration. Derivatives and integrals are inverses of each other. So basically you spend like the first half of AP Calculus doing derivatives, and then you spend the second half undoing what you did the first half of the year. The definition of a derivative starts with the limit of. And so that's why when we start chapter 12, the very first thing in their introduction to calculus that they give us is an introduction to a limit. And so over on page 807, they give us their definition of a limit. It says if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L, and it is written with that notation that you see there in the textbook and that you see here on the top of our note sheet as well. All right, let's make this a little more practical for us. Basically, when we're looking for a limit, we're saying what is the y value approaching as x approaches whatever this number is down here, c, and I need to look at it from both the left-hand side and the right-hand side. So I'm interested in what is my y value doing as x is approaching that designated value from both sides, the left and from the right. So look at example 2. Example 2, we've got the limit as x approaches 2 of 3x minus 2. Now, one thing that is really important in AP Calculus is multiple representation of information. They love to give us a word problem and then have us create an equation that fits that information and sketch a graph of that equation and make a table of values that goes along with that equation or with that graph. They want us using all four of those representations interchangeably. And that's one of the best things about our textbook is from the very beginning, one of the first sections talks about those four multiple representations of information, and it has done that through the entire textbook through the course of the year. So that's fantastic preparation for us for AP Calculus next year as well. So when we approach these limits, we're going to approach them in as many ways possible. We're going to look at them algebraically by using an equation. We're going to look at them numerically with a table of values, and we're going to look at them graphically as well. So when I have the limit as x approaches 2, what I'm saying is, here's my x value of 2 right here. I want to look at approaching that x value from the left-hand side and from the right-hand side. So if I'm approaching that x value from the left-hand side, I might use values like 0, 1, 1.5, 1.9, 1.99, 1.999. And what we find is that the closer we get to the actual number, the more indicative those values are and the more helpful they are. So instead of building a table that's got like 5 or 6 values from the left and 5 or 6 values from the right, we're going to hone in on just those really close values that we mentioned, like the 1.9, 1.99, and 1.999. Same idea from the right-hand side. If I'm at 2 right here and I'm approaching this from the right-hand side, I might use 4 and then 3 and then 2.5, 2.1, 2.01, 2.001. But let's use those innermost values. Let's do 2.1, 2.01, and 2.001. Notice the way that we lay out our table. It just mimics the number line. It's like we're looking at this and saying, okay, let's start 1/10 away and then 100th away and then 1,000th away, and we're at that value. Same idea over here, 1/10 away, 100th away, 1,000th away, and we're at that value. So it's like we're getting a representation of that number line by the way that we lay it out. So if I'm going to go through and plug these numbers in, it's not ridiculously difficult to take 1.9 and throw it in and say 3 times 1.9 minus 2. But if I'm going to do that 6 times on every problem, and I'm going to do like 10 or 15 problems, it'd be nice if there was a faster, easier way to do that. So grab your graphing calculator if you would. Probably the most efficient way to do this is to put your equation in y equals. Now our equation was 3x minus 2. When I took the screenshot, my cursor was sitting on top of the 3, so that is 3x minus 2. And then I'm going to go to my calculate menu, and I'm going to choose option number 1, which is value. And I can go through and tell it, remember, any x value that I want, and it'll generate the y value for me. So the first 2 values that we wanted were 1.9, 1.99, so we could throw those in, 1.9, 1.99, and generate those y values that go along with them. Everybody getting those to work? Okay. So that will probably be the most efficient way to fill in this table. I know typically when we're doing a table, we would use the table feature. The only problem with that is you have to set your table to count by whole numbers or tenths or hundredths or thousandths or whatever, and my table is not consistent here. You know, here it's counting by tenths, here it's counting by hundredths, here it's counting by thousandths, so I would have to constantly change that table set if I wanted to do that. So once you've tried a couple of those and you've gotten them to work so you know that you can get those values correctly, then just go ahead and fill the rest of them in your table. Save you a little bit of time. Now, when I'm recording these values in the table, notice that I'm not necessarily going to include 8 decimal places, but I'm not just going to flat round off to the nearest whole number or the nearest tenth every time. The whole goal of a limit is that I want to see what my y value is approaching. That means it should be changing. It should be getting closer and closer to something. I need to see that change then in my table. So you'll notice instead of rounding every single one of these to the nearest whole number, so it would just be like 4, 4, 4, that's not representing any change. I want to show that, like for this first value, it was 3.7, and then it was 3.97, and then it was 3.997. And a lot of times when I do that, I'll start to notice a pattern. Like it's kind of like if I throw another x into another 9 into the x value, it generates another 9 in the y value, right? So I could pretty much guesstimate if I did 1.9999, what would I get for my y value? Yeah, 3.9997. And so that gives me an idea that if I had 1.99999, I would probably end up with 3.9999997, right? So judging from that, from the left-hand side, what does it appear that y value is approaching? 4. So that would be my guess as well, that from the right-hand or from the left-hand side, numerically, when x is approaching 2, it looks like y is approaching 4. All right, we could have the same kind of discussion from the right-hand side over here. Again, you'll notice that as I put in another 0 in the x value, it generated another 0 in the y value. Now, it won't always do that. It won't always perfectly follow suit like that. But we can typically notice some type of a pattern down here that makes it indicative of what that's going to keep doing if I keep plugging in more and more values, so that at some point I can stop and say, I feel comfortable knowing what this is going to do from here on out. So from the right-hand side, what does it look like these y values are approaching? 4. So I would say then, since the limit from the left was 4 and the limit from the right was 4, I would guess, and that's all it is, it's just a guess, but I would guess that my limit is 4. You can think of a limit like a target or a goal or a bullseye. All parts of my graph should be coming together and converging on that one particular value. So when I come at this from the left-hand side and from the right-hand side, it should be coming to the same place. And if we look at it graphically, we see that. Because, again, I'm approaching 2. So as I approach 2 from the right-hand side, tracing along my graph up here, it does appear to be approaching a y value of 4. And as I come at this from the left-hand side, that would be this part of the graph down here. So as I do that, it does appear to be approaching a y value of 4. So numerically and graphically, we're getting the same answer. Okay, I have a question. If you want to know the y value and you have an equation and the x value, don't you normally just plug in x and get y? I mean, from the very beginning, we had 3x minus 2 and x was equal to 2. So if we just came down here and said 3x minus 2, that would have given us 4, and we could have skipped all that other work. That type of function is called a well-behaved function. How many of those do you think they're going to give us for limits? 1 if we're lucky, right? So, yes, that is true. In that situation, I could have just used direct substitution. And there are times I can do that and come up with my limit. But that's rare. Those types of functions are called well-behaved functions. They're not necessarily rare in the real world, but in the calculus world, they're not going to give us many of those. Most often, they're going to have us analyzing functions that are not well-behaved. So I look at example number 3, and I'm like, ooh, that well-behaved thing was so cool last time when I could just use direct substitution and go straight to my answer. I'm going to try that first. Okay, I plug 0 in the place of x, and I get 0 in the denominator. 0 in the denominator is undefined, right? Can't divide by 0. So does that mean that there's no limit? No, not necessarily. It just means that this limit is not well behaved, and I'm going to have to fall back to making a table of values or looking at a graph or approaching this in some other way because I can't use direct substitution to get my answer. Okay? So this time I'm looking for the limit as x approaches 0. So if I come up here and I think about 0, if I'm using values from the left-hand side approaching zeros, what kind of numbers might you want to use? Okay, if I'm approaching 0, I could go through and say that'd be like -1, -0.5, -0.1, -0.01, -0.001. How about from the right-hand side? Yeah, same thing. 0.1, 0.01, 0.001. And again, remember that the way that we're laying this out is so that it mimics the number line. That when we build our table, we get closer and closer to 0 with each of those values that we fill in. So that we're not doing like a tenth away, a hundredth away, a thousandth away. We don't start over here with that same thing and do a tenth, a hundredth, a thousandth. Notice it's like the reverse of that because it's symmetric. We're trying to center in on 0. Okay, so again, I could use the value feature on my calculator. I'm going to go to y equals, and I'm going to type in that equation. And then I could start plugging in values, like one of the values that we had was 1/10, 0.1. So we could plug that in, and my calculator will generate for me the y value. The nice thing about doing the value button as well is as soon as I put that equation in y equals and I start evaluating for different x values, I also get a picture of the graph, right? So I can eyeball this before I even begin and look at it and go, is this thing even going to have a limit? Or do I have like one piece of the graph shooting up this way and one piece of the graph shooting down this way, and they're not actually all converging on one particular target, one bullseye, one value? I also can get a kind of a guesstimate of what I think that limit might be so that when I'm evaluating it numerically, I can see if my answer makes sense. So if I'm looking at this graph right here and I'm looking for the limit as x approaches 0, what would your guess be? First, do you think you're going to have a limit? Does it look like from the left and the right it's approaching one value? So as I'm approaching 0 from the left and from the right, does it appear to be approaching one value? Yeah. What value does it appear to be approaching? 2. So that would be my guess to begin with. I think my limit's probably going to be somewhere around 2. Let me see what my table fleshes out. All right, so let's go back and build our table. And again, once you've gotten one value off of your calculator so that I know that you're putting it in correctly, then you can just fill the rest of these values in instead of having to take the time to plug them all in right now. All right, so if we look at this from the left-hand side, I've got 1.95, 1.995, 1.9995. What does that look to be approaching? 2. And from the right-hand side, 2.05, 2.005, 2.0005. What does that appear to approach? 2. So if my limit from the left and my limit from the right are both approaching the same value, that means that both sides of my graph would be converging on one target, one bullseye, then I could say that my limit is 2. And sure enough, if I look at the graph, it makes sense as well that from the left and from the right, both pieces of that graph did appear to be converging on a y value of 2. Now, if while you're there on the screen on your calculator, if you go to that value button and you type in x equals 0, do you get y equals 2? No. You get x equals 0, y equals blank, right? There's literally nothing there. That's because that graph does not exist at x equals 0. There's a hole in that graph because there's a 0 in the denominator there. So here's something really unique about limits, and they stress this on the top of page 808. It says, notice that in example number 3, f of x has a limit when x approaches 0, even though the function is not even defined when x equals 0. This often happens, and it's important to realize that the existence or non-existence of f of x when x equals c has absolutely no bearing whatsoever on the existence of the limit of f of x as x approaches c. I will probably say this 20 times in the next week. When I'm looking at a limit, I don't care what is going on at the point. By the definition of a limit on the top of your page, it said, what is y doing as x approaches that value from the left and from the right? I don't care what's going on at the value. I care what is going on as I approach that value from the left and from the right. What's going on at the value itself is irrelevant. So like we saw here, I was able to find a limit of 2 even though there's a hole in the graph right there. The function does not even exist at 0, but I'm able to find a limit of 2 at 0 because I don't care what's going on at the point. I care what's going on as I approach it from the right and from the left. That is my definition of a limit. Look at another one. Example 5, they give us a piecewise defined function. We've seen these before. Piecewise defined function is a function that's defined in pieces. That's where it gets its name. So they tell me if you have an x value that's not equal to 3, your function is equal to 2. If you have an x value that is equal to 3, that function is equal to 0. And they want me to find the limit of that piecewise defined as x approaches 3. All right? So I could go through and say if I'm approaching 3 from the left-hand side, I could use values like 2.9, 2.99, 2.999. If I'm approaching it from the right-hand side, I could use like 3.1, 3.01, 3.001. So if I take 2.9 and I plug it into that function, am I going to plug it into the top piece or to the bottom piece? Into the top, right, because 2.9 doesn't equal 3, and it says if your x value doesn't equal 3, then use this piece of the function. So when I plug in 2.9, I get an answer of 2. How about when I plug in 2.99? Do I get 0 or 2? 2. When I plug in 2.999. And as a matter of fact, all the way across this table, every single value that I'm going to plug in is not going to be equal to 3. So therefore, I'm going to get an answer of 2, right? So if I were giving the limit from the left, what would you say it is? 2. How about the limit from the right? 2, yeah. So since the limit from the left equaled the limit from the right, I would say my overall limit is 2. If I go to graph this function, this is what the graph looks like. For every value except for 3, I'm going to plot the y value of 2. So that would just be a horizontal line at 2 with an open dot right there at 3, because when I'm not equal to 3 is the only time that I have a y value of 2. When I am equal to 3, my y value is 0. So I would come down here and put a closed dot at 3, 0. So again, we go back to that concept of I don't care about what is going on at the point. I only care about what's going on as I approach it from the left and from the right. That function can be undefined at the value, or it can be redefined as a totally different value. It is irrelevant. All that matters is what is going on as I approach from the right and from the left. Both of those values were approaching 2, so my limit was 2. So we've been harping on this idea of a target is a bullseye. It's a goal that all pieces of my graph have to converge on this one particular value. The value from the left has to equal the value from the right. If that did not happen, then I wouldn't have a limit. If my piece from the left is shooting off to positive 2 and the piece from the right is shooting off to negative 2, you tell me what one target they're approaching, what one bullseye, what one value they're converging on. They're not. So in that case, I wouldn't get a limit. And so that's what they tell me here on the top of the page, if the limit from the left doesn't equal the limit from the right, then your limit does not exist. So for the first several examples we've looked at today, we've looked at different ways to get the limit. Now we want to look at what are some of the ways that you might have a function that doesn't have a limit, that its limit does not exist. And so here's the first scenario, and that's when the limit from the left doesn't equal the limit from the right. Now we're going to get some notation for this now that will make this a little more concise. When I have the limit from the left, so I've got the limit as x approaches 0, what I'm going to do is I'm going to put what looks like a little minus sign as an exponent after my number. That indicates that I'm coming from the left-hand side where the negative numbers are. And then the limit as x approaches 0 from the right, I'm going to denote with a little positive sign as an exponent after the number. Now be careful you put it after the number, not in front. Like, let's say this was the limit as x approaches 2. If you put the plus and the minus in front of the number, it would look like the limit as x approaches positive 2 and the limit as x approaches negative 2. So I want to be careful that I put them after the numbers and we put them as little exponents. Okay? So example number 6, they give us a piecewise defined function. No, they didn't. They just gave me one function. Yeah, but they gave me an absolute value. Anytime you have an absolute value, it is going to be a piecewise defined function. Anytime you have an absolute value, it is going to be a piecewise defined function. Why? Because an absolute value is defined by if what's inside the absolute value is greater than 0, you get exactly what you started with. But what if what is inside the absolute value is less than 0, then you get the exact opposite of what you started with. So that's why when we have an absolute value, we're going to have to redefine that into two separate pieces. So I can come over here and say, okay, what's in my absolute value is x. So when what's in my absolute value, x, is greater than 0, it's positive, I just get that exact same thing, x, and my denominator stays the same. So I could even simplify that x over x to be 1. But if what was inside my absolute value, that x, if it's less than 0, meaning that it's negative, I get the exact opposite of what I started with. And so that would be negative x in the numerator and the plain x in the denominator. So that would reduce down to negative 1. So there's my piecewise defined. They asked me to find the limit as x approaches 0. So let's look at the limit from the left and the limit from the right. Same way that we've been doing when we were building our table of values. Here was the limit from the left and here was the limit from the right. All right? So to begin with, I want to check that well-behaved thing, right? It's always worth checking. Doesn't happen very often, but, you know, it's worth a try. So if I'm taking the limit as x approaches 0 from the left, would that be the top function or the bottom function? Approaching 0 from the left. The bottom one, right, because when I'm approaching 0 from the left, here's 0, here's the left-hand side, that would be like negative 1, negative 1/2, negative 0.1, negative 0.01. All those numbers are less than 0, right? So when x is less than 0, I'm supposed to use negative x over x. So that's what I'm going to use. I try that direct substitution. Yeah, it doesn't work. I get 0 in the denominator. So doesn't mean the limit doesn't exist. Just means it's not well behaved. So let's go through and plug in some values. If I plug in negative 0.1, I'm going to have minus a negative 0.1, so plus 0.1, divided by negative 0.1. So 0.1 divided by negative 0.1 gives me negative 1, right. Same story here. If I have a negative 0.01, I can say negative 0.01, so positive 0.01, divided by negative 0.01 gives me negative 1. Same thing with 0.001, that negative 1/1000th. I get negative 1. So what would you say your limit from the left-hand side is? Negative 1, yes. So every one of these is negative 1. I'm going to say my limit from the left is negative 1. So here's my notation for that. The limit from the left-hand side is going to be negative 1. All right, let's try the right-hand side. Process of elimination. We have a pretty good idea. We need to use the other equation for where x is greater than 0, because those are values coming from the right. So coming from the right, I'd be using like 1, 0.5, 0.01, or 0.1, 0.01, 0.001, all of those positive values greater than 0. So using that top equation, x over x. Again, not well behaved. So I can plug in values. What do I get when I plug in 0.1? 1. How about 0.01? Positive 1, same thing for 0.001. So what would you say your limit from the right is? 1. So my limit from the left was negative 1. My limit from the right was positive 1. So what is the overall limit for this function? It does not exist. Why? Because the limit from the left did not equal the limit from the right. And if we graph that, like we literally throw absolute value of x over x into our calculator, this is the graph that we get. And so graphically, it backs up what we just saw a second ago as well. At 0, this graph is not converging on one specific value. I have one piece converging on a positive 1 and one piece converging on a negative 1. They're not all coming together at one specific value. There's not one target or one bullseye here. So that, from my graph, I can see my limit does not exist as well. Now, just as a side note, what if they had given me this exact same equation, but they had said, what's the limit as x approaches 2? If I'm over here at 2, is that limit going to exist? Yes. Because from the left-hand side and from the right-hand side, both pieces are converging on the same value, right? What are they converging on? Positive 1. So that limit would exist for any other value except for 0. Most of the time, they're going to choose the one value from the function that's problematic, and that's where they're going to ask us to evaluate it. Okay. All right, look at the next one. Again, focusing on ways that our limit doesn't exist. So we've seen if the limit from the left doesn't equal the limit from the right, the limit doesn't exist. Here's another way the limit doesn't exist. For this one, I've got the limit as x approaches 0 of 1 over x squared. So I try to do direct substitution. Of course, it doesn't work. So I build a table of values using those same x values that we've been using all day long when we had 0. And I start plugging them in, and I start getting like crazy answers. Like if I have a negative 1/10, negative squared is positive, 1/10 squared would be 1/100th. So 1 divided by 1/100th would be 100. All right, then I've got a negative 1/100th. So if I plug that in, 100 squared, it has 2 zeros, so you square it, you get 4 zeros, right? 1 divided by that, I'm going to end up with 10,000. Negative 1/1000th, that one had 3 zeros, so when I squared it, I ended up with 6 zeros. So 1 divided by 1/1,000,000th gave me 1,000,000. So I can only imagine if I go through and I plug in like negative 0.000001, I'm going to get a number that I probably can't even pronounce down here, right? So as I'm looking at the limit as x approaches 0 from the left-hand side, what does that look to be doing? Yeah, it's continuously getting larger and larger and larger without bound, and so yes, it's going to infinity. So absolutely, I could say that that limit from the left-hand side is getting infinitely larger without bound, and so I could use a symbol for that for infinity. The exact same thing happens on the right-hand side, because if you square a positive number, then, or square a negative number, you get the same thing, right? So I could go through then and say, if I plug in these values on the right-hand side, every one of those I get the same thing. I could also say then that that's going to infinity. Infinity is not a number. Infinity is a symbol that represents the concept of something getting infinitely larger without bound. The only way that I can say I have a limit is if I can walk up and put my finger on this one point right here and say, at this one value right here, everything converged on this target, on this bullseye, on this goal. That is my limit. I can't do that with infinity. And so for that reason, if any part of my limit from the left or from the right, if any part of my limit goes to infinity or negative infinity, then my limit does not exist. Now, it used to be in AP Calculus that they would want us to write that answer as does not exist. But they changed that several years ago, and now the answer that they want us to give is infinity. They are very careful to point out we're not saying that we think infinity is a number and that your that both sides of your graph are converging on this one particular number. Here's what they're saying. If I asked you, do you have a pet? And you said, yes, I have a dog. Or you said, yes, I had a German Shepherd. That's not two contradictory answers. But one's a more specific answer than the other, right? So, if we're looking for specifics, that might be a better answer to give the type of dog you have. It's the same idea here. If I say my limit doesn't exist, or I say my limit is infinity, when I say my limit is infinity, I'm just giving a better answer, because what I'm saying is my limit doesn't exist, and the reason it doesn't exist is because my function is going to infinity. So for that reason, AP has switched that now they want us to give infinity or negative infinity, whatever the case may be, as our answer instead of does not exist. But that may vary from textbook to textbook, so you may see it different in a different book. And again, if we looked at the graph of this, the graph of that would reiterate what we thought, because as you approach 0 from the left-hand side, it shoots off to infinity, and as you approach 0 from the right-hand side, it shoots off to infinity. Example 8 gives us another way that a limit might not exist. All right, again, I tried direct substitution here. I plug in 0, I get undefined, so I'm going to have to go about this a different way. And in this case, we have the table laid out for us here. So I go through and I plug in the values that are given to me, and I can't get my y value to settle on any one particular point. Up until this point, it was always very clear the values were converging on a specific value. That's not happening here. It's oscillating back and forth between 1 and -1. So if it will not settle on a particular value, then I'll say that my limit doesn't exist. If you look at the graph of that one, it's really helpful because it helps us understand a little better what we're looking at. So I'm going to put sine 1 over x into my calculator. I'm going to make sure that I'm in radian mode, and I'm going to do a zoom trig because that's usually my default when I start with a trig function. So I was in radian mode, I typed in sine 1 over x, I went to zoom trig, and this is what I got. Now, I'm trying to see what's going on at 0, and I couldn't really tell what was going on there. So I went to zoom, and I zoomed in a little bit, and I still can't tell what's going on. It's just like a great big mess right there in the center. So I'm going to shave off some of my x values over here and some of my x values over here. I'm going to go into my window and tell it just to go from -0.2 to +0.2. Let me get a really close-up view of what's going on here. And when I do, I still just get more craziness. Because what's happening is I have an infinite number of oscillations in the center of this function. The closer and closer I get to 0, this graph doesn't change. I can keep resetting these x values to be smaller and smaller and smaller all that I want, but I'm going to have an infinite number of oscillations back and forth between 1 and -1. Since my graph is not converging on one particular value, then my limit does not exist. So that's another way that your limit doesn't exist. Limit from the left doesn't equal the limit from the right. Your limit goes to infinity or negative infinity, or your limit doesn't settle on one particular value. Now, I don't want you thinking that every time you see a trig function, it's automatically going to be the limit doesn't exist. Like, if you look at this example, we've got the limit as x approaches 0 of sine x. This function actually ends up being well behaved. When I do direct substitution, I get 0. If I make a table of values, all the values converge on 0. If I look at the graph from the left and from the right, both pieces of the graph are settling on one specific value. They're settling on 0. So not all trig functions will be that way. It was just that particular one. All right, so what we have done today is get an intuitive understanding of limits, because they're going to start now giving me some properties and some algebraic ways that I can calculate limits. Man, is that helpful, because building tables and looking at graphs, it's a great resource, but it's very time consuming, and literally I'm just guessing what the limit is from those things. I don't have a precise definition. I'm making an educated guess, but it is still a guess. So it would be nice if I had a concrete algebraic way of doing this. And so that's what they start giving me on page 811. They give me some properties of limits. The first one says that if you have the limit as x approaches any number c that is a real number of some constant b, then your limit will be that constant. The limit of any constant is always going to be a constant. Here's an example. If I had the limit as x approaches 2 for 7, the limit of any constant will be that constant. It does not matter what this number is down here. Why? Because think about what that graph would look like. If you graph y equals 7, that's a horizontal line at 7. So if you're over here approaching 2 from the left and from the right, it's going to be at 7. If you're over at 523, approaching from the left and from the right, you're still going to get 7. If you're at negative 3,265.476, approaching from the left and from the right, you're still going to get 7. So the limit of any constant is always going to be that constant. All right, then the next two properties they give me tell me that if I have the limit of x, it's well behaved. I can just use direct substitution. Remember we saw that at the very beginning of the lesson, that when you can take a number and plug it into the function and get the limit, it's called well behaved. What they've told me here is that x is well behaved. Because think about what the graph of x looks like. It's that diagonal line that goes through 0, 0, 1, 1, 2, 2. There's nothing funky going on with that. There are no holes or skips or jumps or craziness in it. Wherever you approached from the left and from the right, you would get the y value associated with it. They also tell me that that's true not just for x to the first power, but for x raised to any power. So if I had x to the second, or x to the third, or x to the 23rd, I could just use direct substitution. And number 4, they tell me that this is true for some radicals. They tell me that if you have the limit as x approaches c of the nth root of x, you can just use direct substitution as long as if you have an even index, like if this is a square root or a fourth root or something like that, that what's under here has to be greater than 0. It can't be equal to 0 or negative. It would have to be greater than 0, and we'll spend more time on that later on. All right, so we get down to example number 9, and now we get to use these properties. So for example number 9, it says the limit as x approaches 4 of x squared. Well, that's just this third property right here, right? So I can use direct substitution and say, okay, I can plug 4 in for x. 4 squared is 16. I don't need a table. I don't need a graph. That's a happy thing. I get to b. b says the limit as x approaches 4 of 5. What's the limit of a constant? That constant, right. So that limit would be 5. All right, then they give me a few more operations on the bottom of 811. They tell me that you have a sum or difference property. That says that if you have the limit of two things being added or subtracted, you can take the individual limits and then add or subtract. So that means I can go through and say, okay, the limit of x squared, hey, I did that a second ago. That was 16. It's just the 4 squared. I can do direct substitution. The limit of a constant, that negative 5 right there, or subtracting 5, would just be 5. And this middle piece right here has a constant times a variable. That's our scalar multiple property there on 811 that says if you have a constant times a function, you can take the limit of that function. So we could take the limit of x using our property up here for direct substitution and then just multiply by that constant. So I found this limit and this limit, they were being added, so I go back and add them. I found this limit and this limit, they were being subtracted, so I go back and subtract them. So we just proved by those properties that all polynomials are well behaved. So from here on out, when I see a polynomial, I get to just do direct substitution. So when I hit a fraction is just a polynomial divided by a polynomial, right? So they give me a product rule and a quotient rule here that tell me if you have a product or a quotient, you can find the individual limits and then multiply or divide. So in this case, I can say this is a polynomial, it's well behaved. This is a polynomial, it's well behaved. I can do direct substitution, and now that I have those two limits, I just divide. Okay? So those properties will make our life much simpler. So here's our homework for tonight.